Bismillahirrahmanirrahim. Welcome to the class Mathematical Methods for Physics. My name is Dr. Salim Ahmed and I'm Assistant Professor of Mathematics at Comsats Institute of Information Technology. I will be teaching you this course for this semester which is Mathematical Methods of Physics. The course code is MTH483 which is being offered in MSc Mathematics. I hope we'll go along well for the whole semester, and I hope you will understand whatever I'm teaching. I will be teaching. So a little bit about me, a little bit introduction about me. My name is Dr. Salim Ahmed. I'm Assistant Professor at Comsat Institute of Information Technology, Islamabad campus, and I have been working there as Assistant Professor since December 2011. About my education, I have done my PhD from State University of New York, USA. Before going to America, I have done MSc and MPhil from Quaid-e-Azam University in the years 2000 and 2002 respectively. So this was a little introduction about myself. A little introduction about the course. What is the motivation behind studying this course at this level? The course introduces a variety of mathematical methods essential for technical proficiency in advanced courses of mathematics, theoretical physics and engineering. The class will focus on developing both the understanding of basic techniques and skills in their application. The objective of this course is to provide an introductory overview of linear, integral and partial differential equations and the integral transform as they apply in engineering and physics problems. So basically we'll be studying two sides of the equations, integral equations and the differential equations. We'll go into details of both the topics here, and then we will study integral transforms as well. You might have seen them before. You definitely have seen partial differential equations and maybe somewhere integral equations as well and their transforms. Basic physical laws are reviewed and applied to the derivation and interpretation of initial and boundary value problems. So in physics, whenever you deal with the basic physical laws, and when you apply and interpret them, you usually get initial and boundary value problems. For example, differential equation with the initial conditions or differential equations with the boundary conditions. So respectively they are called initial and boundary value problems. So this is the motivation behind the course, behind studying this course. Let's go over some main objectives of the course, what we will be getting out of this course at the end. First of all, to provide students with basic knowledge of integral equations. So this will be our first objective. Basic knowledge of integral equation. We will not go into very detail of this integral equation because this is a whole course in itself. So we will not be studying the whole course of integral equations. We will definitely go into little bit details and give you the idea what integral equations are, how they arise in our problems, in our physical problems or mathematical problems, whatever we are dealing with. Of course, we'll be getting some integral equations, so how to deal with them. There are certain type of integral equations, we will go through them as well. Secondly, to introduce the methods that permits the determination of maximal and minimal values of the functions. This will be our second objective of the course. The third one is to show students how to formulate physical problems in terms of partial differential equations. So first it was integral equations, then we went on to maximal and minimal values of the functionals, and then we will go towards partial differential equations, how to formulate physical problems in terms of partial differential equations. You might have seen them before in your physics courses or maybe mathematical courses as well. Whenever you deal with some physical problems, usually you get derivatives involved, and whenever you get derivatives you get some kind of differential equations, and if you are looking for the derivative with respect to more than one independent variables, you will usually get the partial differential equations. The fourth objective is to provide students with a basic knowledge of Fourier series and separation of variables and integral transforms. So basically there are three things in here: Fourier series, method of separation of variables to solve the partial differential equations. Basically, Fourier series will be the prerequisite for the separation of variables. If you don't know Fourier series, we cannot apply completely the method of separation of variables to partial differential equations. And then we'll study integral transforms as well. Sometimes we take the transforms of the differential equation to convert them to different forms. And at the end of the semester, at the end of the course, we might study the solutions, series solutions of the differential equations as well. So we will be dealing with integral equations, we will be dealing with differential equations, and we will be dealing with both the partial and the ordinary differential equations. All right, and then of course these are the tools we will be using: the Fourier series, the integral transforms, the series solution, what is the power series, and things like that. So we will review them, of course. If you have studied them before, no problem at all. I'll be going through everything, whatever we are using. I'll try my best to explain them to you so that you can get the essence of every topic in this course. So what are the course contents? This is the first lecture, so I should introduce you the course, the whole course. Actually, in these 4 objectives, you are basically looking at the brief summary of the course. So let us get into more detail of the course contents. What are actually the course contents? So first of all, we will study linear operators. Secondly, integral equations of Volterra and Fredholm types. As I said, we will be starting with the integral equations. So first of all, there are very basic 2 and famous 2 equations, integral equations, that are called Volterra and Fredholm types. Introduction to calculus of variation of one variable, Euler-Lagrange equations, Euler-Lagrange formulation, whatever you want to call it. Solutions of partial differential equations by Green's functions. This is another topic. Boundary value problems, how to deal with them. Solution of partial differential equations by separation of variables. Fourier series, of course we need Fourier series to completely determine the solution of PDEs via separation of variables. Laplace and Fourier integral transformations and their applications to solve ODEs and PDEs. As I said, both are integral transformations. So we will be dealing with Laplace transform and Fourier transforms only. There are more integral transforms as well. But if you take the course, maybe partial differential equations or something like that, you may get more. You may get to see more detailed integral transforms and more integral transforms, not just Laplace and Fourier. But in this course, we'll be dealing with only 2, Laplace and Fourier integral transformations. Orthogonal functions and solution of Sturm-Liouville system of equations. Orthogonal functions, again, when we'll be dealing with Fourier series and stuff like that, you will get to see orthogonal functions and these type of things. And solution of SL boundary value problem basically is a Sturm-Liouville. We cut it short and say that SL boundary value problem. Lastly, series solution methods of ODEs, and in their applications we will be studying Bessel equations, Legendre's and Hermite polynomials, etc. All right. So in ODEs, I don't know whether you have taken a good course in ODEs or not, but in ODEs, if you have seen the solutions, the series solutions, then you must have seen Bessel equations, Bessel functions, Legendre equations, and Legendre polynomials, Hermite polynomials, etc. All right. So this is the brief, rather detailed course content summary, what we'll be studying in this whole course. All right. Recommended books for the course, there are many written for mathematical methods for physics. One which is very famous is of Orfken, G. Orfken, Mathematical Methods for Physics, Academic Press, Boston, 1985. It's a very old book. We have a newer version as well, which is this one, G.B. Orfken and H.J. Weber. They have both written this one, Essential Mathematical Methods for Physics, Academic Press, San Diego, 2003. So 1985 is basically the older version, but it's a very, very basic, and people use it as a textbook for this course. So of course you'll get a lot of help from that book. And if you want to buy a newer version, that's fine. These are recommended books. I will be making notes for you guys. My slides will be very comprehensive, so you can get a lot of help. I'll be consulting all these books to write down your notes. So if you want to buy some of them, it's fine. There is a local author as well, Khalid Latif Mir, Mathematical Methods for Physics. It's easily available in the market, and it's cheap as well. Of course, a local author. So Khalid Latif Mir has also written this book, Mathematical Methods for Physics. You can buy that if you want. I'll be consulting that book as well. And then for partial differential equation, the second part of the course, both the first three books they contain partial differential equations as well, but there are more comprehensive books on partial differential equation, which is Richard Haberman, Elementary Partial Differential Equations, Shankara Rao, Introduction to Partial Differential Equations, and these are the textbooks being used in different universities in Pakistan and all over the world as well. So Richard Haberman is a very good book for partial differential equations. You can consult these 5 books. There are more books. You can go to libraries, you can search for Mathematical Methods for Physics, or maybe you can search for integral equation books, differential equation books, partial differential equation books, Bessel equations books, whatever. You can find the books and read. The more you read, the more concepts you get cleared. All right. So of course, it's a very good habit to read books, not just rely on one guy's notes only. All right. Although they will be very comprehensive, but I will definitely recommend you to go over more books if you can. After that, what is the grading scheme? If you have taken the courses here at Virtual Campus before, you must know what is the grading scheme. Quizzes consist of 10%. There will be 4 quizzes in the semester. They will constitute of 10% of your overall grade. Assignments also contain 10% of the overall grade. There are graded discussions, 5% of them. So graded discussions are basically, I will give you the topics, you will sit together and discuss. You will ask questions among each other. I will be just observing you, what you are doing with this topic, what type of questions you are asking, and how you guys are answering your peers' questions. All right, so that will be graded discussion. 5%, midterm 25%, final 50%. So if you see 10% plus 10% plus 5% plus 25%, so 50% internal grading. Before final exam, you will have 50% of the internal grade. Whatever you get it, and then you will have 50% of your grade in the final terminal exam, which will be, of course, a lengthy exam. So that's our grading scheme for the semester. So in today's lecture, we will be studying linear operators, integral equations, classification of integral equations, special kinds of kernels, helping tools for integral equations. So this will be our scheme for today's lecture only. All right, so we'll be starting with linear operator. So let's see what the linear operator is. A linear operator L, by definition, satisfies L acting on C1U1 plus C2U2 is equal to C1 LU1 plus C2 LU2 for any two functions U1 and U2 where C1 and C2 are arbitrary constants. So basically, linearity is the same everywhere. If you are applying your operator on a linear combination of two functions, U1, U2 are two functions, linear combination is C1 U1 plus C2 U2. If you are applying linear operator on them, it will give you the linear combination of linear operators on U1 and U2. So first you apply L on U1, L on U2, and take the linear combination. So basically, C1 comes out, L operates on U1, plus C2 comes out, L operates on U2. If any operator satisfies this definition, it will be called a linear operator. After that, partial by partial t and partial 2 by partial x squared. These both operators. First is the first partial derivative, second one is the second partial derivative with respect to x, are the examples of linear operator since these two satisfy above equation. It's very easy. If you take the derivative of the linear combination, you get the linear combination of the derivatives. So it's a linear operator. This is the proof. It's very easy. Nothing to be explained. Partial 2 by partial x squared. It's again very easy. Derivatives go straight to the functions. It doesn't bother C1 and C2, and plus sign as well. So it preserves scalar multiplication and addition. So any operator that preserves scalar multiplication and addition, it's a linear operator. Note, any linear combination of linear operator is a linear operator. So if you have one linear operator like partial by partial t, second linear operator, which is partial 2 by partial x square, and if you add them up or get any linear combination of these two operators, any linear combination, that will also be a linear. If you take partial by partial t plus partial 2 by partial x square, let's call this L. This is our operator. Apply this on C1 U1 plus C2 U2. You will definitely get C1 L U1 plus C2 L U2. It's very easy. You can do it by your hand and do it right now maybe. Alright, you can see whether this is a linear operator or not. However, if you take the square of partial by partial t square will not give you the linearity. It will become a nonlinear operator. It will not be a linear operator. You can see it very easily. To prove the nonlinearity of the operator partial by partial t squared, we do the following calculations. In our case, what is L? Our linear operator L is partial by partial t square. It's not the second derivative, it's square of the first derivative. Then Lu is partial u by partial t whole square. So your operator is acting in two steps. U goes to partial u by partial t. So first you are taking the derivative with respect to time, and then you are taking the square. So this is a two-step operator basically. You start from u, go to the derivative, and then the square of the derivative. So if you apply this L on C1 U1 plus C2 U2, you have to take the derivative and then the square. If you take the derivative, you get this thing, C1 U1 plus C2 U, C1 partial U1 by partial t plus C2 partial U2 by partial t, complete square. If you take this, open the square, you will get this. Alright? You can bring the C1 square out, C2 square out. So this is the final form you are getting. But if this was a linear operator, you should get this thing. You should get just C1 and the square of partial U1 by partial t plus C2 square of partial U2 by partial t, but we are not getting that. There is no way this last two equations can be equal. There is no way these last two expressions can be equal. So it means the left hand side, very left, this one, is not equal to the right hand side, so this is not a linear operator. Alright, so this was an example of the linear operator. Next is integral equations. What are integral equations? If you have seen them before, very good, but we'll be going through it again, so I will tell you very basics of this thing, so you don't have to worry about anything. Integral equations, basic definition: any equation that contains unknown function under one or more integral signs. You know what the differential equation is? Any equation that contains derivatives is called differential equation. So any equation that contains integrals, unsolved integrals, is called integral equation. So formally what we can say that an integral equation is an equation in which an unknown function u of x appears under one or more integral signs. Of course, if it is appearing in integral sign, it means it is an integral equation. There are unsolved integrals in there. An unknown function should be in there. Alright? For example, the equation is an integral equation. You see ux is appearing here inside the integral sign. A to b kxt. Kxt may be a known function, but ut is not a known function. It's an unknown function to be determined, is equal to f of x. Second example, ux minus lambda times this thing is equal to, again see ux is outside of the integral, but it is inside as well. Ux is outside, ut is inside. It means u is a function of x and t both. Alright? It's an unknown function of x and t appearing in one integral sign. It's an integral equation. Third, ux minus lambda kxt ut cubed dt is equal to f of x. They look same, all of them, but of course they are a little different. Here you see it's ut cubed, so that's only making it non-linear, nothing else, but all these equations are the examples of integral equations. Here fx and kxt are known functions, lambda a and b are constants. Right hand side fx is a known function, kxt is a known function, only ut, ux, they are unknown, because there is only one unknown in an equation. So if you can solve it, you will solve it for u, not for k or f. K and f are given functions. Alright, they are given and known functions. Alright, next is classification of integral equations. So how to classify integral equations as linear or non-linear. An integral equation is linear if it satisfies the linearity property. Of course, anything is called linear if it satisfies linear property. So whether it is integral equations or anything else. All right. So if u1 and u2 are solutions of a given integral equations, then c1 u1t plus c2 u2t is also a solution of the given equation. For example, ux is equal to a to b kxt ut dt. Ux is equal to lambda a to b xt ut dt plus fx. If you look at the previous three examples, these are the first two examples. I gave you three examples of integral equations. The first three are linear. First two are linear. Non-linear integral equations, an integral equation which is not linear, it is said to be a non-linear equation. Of course, if it does not satisfy the linearity property, we will not call it linear equation. So if in that case, it will be called non-linear equations, non-linear integral equation. So this is the example where you are getting non-linear integral. You see, u is appearing inside the integral as square, u square of t. So whenever you get more than one power of anything, unknown function, more than one power is appearing in your equation, it is said to be a nonlinear equation because it will not satisfy the linearity property. Here the term u square t inside the integral confirms that the equation is nonlinear. If u1, u2 are solutions of the above equation, then the linear combination of these two functions does not satisfy the above equation. Alright, so if u1, u2 are the solution, its linear combination may not be the solution of this equation, so that's why it is not satisfying the linearity property. Its solutions are not satisfying the linearity property. So there are two types of differential integral equations: classification as linear, classification as non-linear integral equation. We then have a singular integral equation as well. What is that? A singular integral equation is defined as an integral equation with the infinite limits. So first case is if you get the integral limits as infinite, then it is a singular integral equation. Or what is the second case? Or when the kernel kxt, the function appearing inside the integral kxt, we call that function a kernel. That's why we call it kxt, k for kernel. Kernel of the integral becomes unbounded at any certain point inside the interval. Alright, so there are two things: either limit should go to infinity or your kernel becomes unbounded. So see, in first example, you are having infinite limits in integral equation. You see, this one, in integral minus infinity to infinity kxt ut dt. This is integral equation with infinite limits, so this is a singular integral equation. Second equation, this is your kernel. Kernel is given 1 over x minus t power alpha. This is alpha ut dt. Alright, so now you see at x is equal to t, because your t goes from 0 to x. Right? T goes from 0 to x. So when t will become x, x minus x will become 0. 1 over 0 will give you infinity. So this kernel becomes unbounded at the limits. Alright? So if you have seen the improper integrals, the same definition applies here in integral equations. Either your function becomes unbounded or your limits are unbounded. Limits are infinite. Then your equation will be called singular integral equation. Alright, so as I mentioned before, two basic type of equations are Volterra integral equations and Fredholm integral equations. Any equation that has that type will be called equation of Volterra type or equations of Fredholm type. Alright, so the most standard form of the Volterra integral equation is given by the form phi of x ux is equal to fx plus lambda a to x kxt ut dt. So right side you have fx plus lambda and an integral which contains ut dt in it. Alright, and left hand side you have ux, but some function may multiply this ux as well. In general, you may have ux on the left hand side. In that case, phi of x will be equal to 1. But you can have phi of x something else as well. You can have x, x squared, sine x, cosine x. Any function of x can be there with ux on the left hand side. That's why we wrote the general form of the Volterra integral equation, where the limits of integration are function of x and the unknown function ux appears linearly in the integral sign. So basically it's a linear integral equation, because you see ut and ux everywhere they have just one power. So it's a linear integral equation. Only thing here is, see the limits. In the limits you have x in there from a to x. Alright, that's why this is the only thing to be noted here. So we can further classify Volterra integral equation into the following three types: Volterra equation of first kind, Volterra equation of second kind, and homogeneous Volterra equation of second kind. So there are three further classifications of Volterra integral equations. Volterra equation of first kind. What is that? A linear integral equation of the form fx plus lambda a to x kxt ut dt is equal to 0. So what we have done with the general form of the equation, we have taken this phi x to be equal to 0. I said phi is a function of x. It can be anything. It can be 0, it can be 1, it can be x, it can be x squared, it can be any other function of x. If you take phi x equal to 0, you will get the Volterra equation of first kind. That's basically an easier form of the equation. Fx plus lambda a to x kxt ut dt is equal to 0 is known as Volterra equation of the first kind. What is Volterra equation of the second kind? Second kind is when you take here, when you take phi x equal to 1, the next simplest possibility. The first one was take phi x equal to 0, get rid of it. Second is, okay, if you want to have it, take it 1. Phi of x is equal to 1. If phi x is 1, you will get the Volterra equation of second kind. So let me show you this one. A linear integral equation of the form ux is equal to fx plus lambda kxt ut dt. This is the Volterra equation of second kind. If you compare with the general Volterra equation, phi x has been taken to be 1. So first case we took phi x equal to 0, in the second case we took phi x is equal to 1, and we got respectively Volterra integral equation of first kind, Volterra equation integral equation of second kind. And then we have homogeneous Volterra equation of second kind. This is the Volterra equation of second kind. If you take this f of x, any term without u, you see left hand side has ux, in right hand side the second term has ux in it. So any term without f of x, without any u, makes it homogeneous and non-homogeneous. If there is a term fx, it's a non-homogeneous. If I take this fx to be equal to 0, if it's not there, then your equation will become homogeneous, and you can write it like that. If phi of x ux is equal to lambda a to b kxt ut dt is called the homogeneous Volterra equation of second kind. Because second kind reason is left side is not 0. In first kind we have taken left side to be equal to 0. So if there is ux term there, still there, it's of second kind. Alright, so let me summarize this again. Volterra integral equation of first kind does not have ux term in it, only fx plus integral term. Alright, Volterra equation of second kind does have this ux term, but phi x is 1 there. Only ux equal to fx plus the same thing. This left hand side, if you replace the right hand side 0 thing equal to f of x, it will become the second kind. And then we have homogeneous where we taken fx equal to 1. So if there is no fx term or no term free of u of x, alright, it's called a homogeneous integral equation. The second most popular integral equation is Fredholm integral equation. If you look at this equation which is written in front of you, the most standard form of the Fredholm equation is given by phi x ux is equal to fx plus lambda a to b kxt ut dt. Now you must be wondering what is the difference between Volterra equation and the Fredholm equation. They look the same. Only difference is here, you see, b, it's a constant limit here, but in Volterra equation we had x in there, where the limits of integration a and b are constants, whereas in Volterra equation we did not have them to be constant. We had a to x. The second limit, upper limit of the integral was x, not b. Alright, so you can say that the interval of discussion in Volterra equation is x greater than or equal to a. That's it. We don't have upper limit. X can go till infinity. We don't know. A to x. What is x? We don't know. But here, your x is defined within a closed interval a to b. You are going from a to b. That's it. So where the limits of integration are constant and the unknown function appears linearly under the sign. Every other thing is the same. In Volterra and Fredholm equations, every other thing is the same. Only the upper limit in the integral sign is constant, b here. And in Volterra equation, it was x, not the b. We can, as we did with the Volterra equation, we can further classify the Fredholm integral equation as well. Fredholm integral equation of first kind, Fredholm integral equation of second kind, homogeneous Fredholm equation of second kind. Exact three classification as was the case with Volterra. Alright, so again, if we take phi x equal to 0, it will give me the Fredholm equation of first kind. If I take phi x equal to 1, I will get Fredholm equation of second kind. And if you take fx to be equal to 0, I will get a homogeneous Fredholm equation of second kind. Alright, once again, exactly the same classification as we did with the Volterra equation, exactly the same classification. Here you see, only the difference is, let me show you those slides as well. Let's see these three slides. You see, this equation, and this equation, all are the same as the Fredholm one, but only difference is coming in the limits. Here it was x, here it was x, and here it was x. Alright, but in Fredholm equations, only difference is we are getting the limits from a to b in your integral sign. Sometimes in literature, we get to see the mixed equations. Some terms contain the derivatives of unknown function, and some terms contain the integrals of the unknown functions. Alright, these are called mixed equations or integral differential equations. Not just differential equations, not just integral equations. They are called integral differential equations. By name, it's very clear that integrals are there, derivatives are there. That's why we are having integral differential equations. An integral equation is said to be integral differential equation if the unknown function ux appears as the combination of ordinary derivative and under the integral sign as well. So in examples, you can see the left hand side, instead of ux, you are getting the derivative of ux. If you compare this is a Volterra type equation. Volterra type equation, right hand side is fx plus lambda 0 to x. Right? So Volterra type equation, but left hand side is not just u of x. It's not just ux, it's the second derivative of u with respect to x. That's why it's not Volterra equation, it's not an integral equation, it's not a differential equation, it's integral differential equations. Similarly, in the second one, you have Volterra type right hand side. If you look at the right hand side, it's a Volterra type equation, 0 to x, and kernel is sine x minus t. Your kernel kxt is sine x minus t in this case, but the left hand side contains derivatives of u. d2u by dx square plus du by dx. So these are two derivatives given on the left hand side. So whenever that happens in an equation, that you are getting the integral signs as well, you are getting the derivatives as well of unknown functions. Integral of unknown, derivative of unknown functions, that is called integral differential equations. Let's say if on the left hand side there is no derivative, it's just u, and you take the derivative of fx, f prime of x, then it will not be called integral differential equation. The reason is you are interested in the derivatives of the unknown function u of x, not of f of x. Fx is a known function. If you take the derivative, it's another known function. Derivative, you can call it g of x. So nothing changed. It's still an integral equation. Alright? So whenever u is replaced by its derivative on the left hand side, that becomes integral differential equation. Unknown function has to be differentiated, not the known functions. Alright? Right hand side, if you see here, these are the initial conditions related to the equation. The reason is, when you have the derivatives, whenever you have the derivatives, you write conditions with them. Two derivatives are given, you need two conditions. First is u of 0 and second is u prime of 0 is given to you. And these can be any conditions. If I don't write these conditions, that's fine. These equations are still called integral differential equations. Alright? So we have studied so far the linear operators, the integral equations, and classification of integral equations. In classification, linear, nonlinear, singular, Volterra and Fredholm types equations. We have seen kernels in our integral equations. Whenever you write integral 0 to x or a to b, whatever you are writing, you see kxt inside appearing in the integral equation. If there is kxt in the integral equation, that is called a kernel, and we can study different types of kernels as well. Some special types of kernels, special kinds of kernels. Alright, so that will be our next direction where we are heading to. What are those special kinds of kernels? Does it make any difference? What happens if we just write k of xt to be any function? What will happen to the integral equation? Alright, so these are important questions basically. First question is, how important is this kernel, kxt? How important? Alright, if it is important, what type of functions are considerable? Or any type of function is considerable? We can consider any type of function. What are the difficulties we will be facing with this kernel? What is the benefit of considering some special kinds of kernels? So these are all questions. They must be arising in your minds as well. Alright, so let's discuss some special kernels which will be helpful in our study of integral equations. First is symmetric kernel. What is symmetric kernel? A kernel kxt is symmetric if kxt is equal to k prime tx, not k prime, k bar tx, where the bar denotes the complex conjugate. If you take the conjugate of this kernel and then you reverse the order of xt and tx as well. See, two things are happening. Here it's kxt, here it's tx, and we are taking the complex conjugate as well. If kx is a real function, then conjugate will not make any difference. Then you have only to swap k and t and k. If you swap x, t, x, and nothing happens to the kernel, it's a symmetric kernel. But if it's a complex function, then you have to see both things, conjugate as well as the swapping of t and x. If both changes will not change the kernel at all, then the kernel is said to be symmetric. Alright, examples of the symmetric kernel are sin x plus t. Now sin is a real function. Take the conjugate, nothing happens. So forget about conjugate here. If you change x and t and x, will anything change here? Sin x plus t and sin t plus x are exactly the same things. Nothing happens to the kernel. It's a symmetric kernel. Second, x squared t squared plus xt plus 1. Again, it's a real function. It's a real kernel. Swap t and x, nothing will change. X squared t squared is the same as t squared x squared. xt is the same as tx. So their sum is also unchanged. It's a symmetric kernel. Third is complex. You see, iota times x minus t. Iota times x minus t. Now complex conjugate will affect this function. Take the conjugate. What will happen when you take the conjugate? If you recall, the conjugate changes the sign of iota. If you take the conjugate of this whole thing, iota will be replaced by negative iota. And then replace t by x and x by t. Swap them. X minus t will become t minus x. Take minus common. Negative and negative iota again will become plus iota, and you will get x minus t inside. So third kernel is also symmetric. The reason is iota becomes minus iota and x minus t becomes t minus x. So again, if you simplify, you get the same kernel back. It's symmetric kernel. Second kind, and any kernel which does not satisfy this condition is called asymmetric or non-symmetric functions. They are not symmetric kernels. All right. Next is separable or degenerate kernels. What are the separable kernels? What are the degenerate kernels? A kernel kxt is called separable if it can be expressed as the sum of finite number of terms, each of which is the product of the function of x only and a function of t only. If you can write any function kxt as a product of one function of x, one function of t separately, then it's a separable function. And you can have finite number of terms like that, not just one term. You can have 2-3 terms where in every term you have a product of two functions. One function is of x, second is function of t only. All right. So here you see phi of x and psi of t. You see, one is a function of x, second is a function of t. All right. So you can have a finite number of such terms. All right. If any kernel can be written like this, is called a degenerate kernel or separable kernel, because you are separating x and t variables. You are separating them. All right. So if you are able to do that, your kernel will be called separable or degenerate kernel. Difference kernel. Another kind of kernel is difference kernel. Difference kernel is kxt is represented as the difference of x minus t. Any function where x, t are appearing as a difference. That kxt is x minus t. Kxt is 1 over x minus t. Kxt is 1 over x minus t square. All these kernels are called difference kernels. The reason is your x and t are appearing as the difference. They are not appearing separately. They are only appearing as a difference of these two variables. So a kernel is called difference kernel if it is dependent solely on the difference x minus t. All right, and that is kx minus t is equal to kt minus x. So it's a difference kernel. Any such kernel is called a difference kernel. Next special kind of kernel is iterated kernel. Iterated kernel. The iterated kernels k and xt, n goes from 1 to 3 so on, for a Volterra integral equation are defined as follows. k1xt is kxt, means just call k1xt is kxt, any known function. k2xt will come from k1, k3 will come from k2, k4 will come from k3, and so on. All right. So here you see knxt is coming from kxz and kzt. You see, k0, when you take n is equal to 1, it's k0. k0 means nothing. All right. It should be 2, 3, 4, 5 because we defined k1t separately. So k2xt will have kxz times k1zt. So if you replace k1 here, simplify it, it will give you k2. Similarly, replace k2 here, you will get k3. Replace k3 here, you will get k4. So iteration is going on. That's why we call it iterated integral. You are getting k2 from k1, k3 from k2, k4 from k3. So whenever this type of situation happens, it's called iterations. So these kernels are coming from iterations. That's why they are called iterated kernels. All right, iterated kernels. Why we are calling it iterated kernels for a Volterra integral equation? The reason is in integral sign here you see it's from t to x. It's from t to x. Z goes from t to x. So if you fix them, not t to x, rather from a to b, all right, limits are constant, you can call it a iterated integral of Fredholm type. All right. Similarly, Volterra and Fredholm are very similar. Similarly, we can define iterated kernels for Fredholm integral equations. For Fredholm integral equations as well. Of course, they are very simple. Only we need to change the limits. All right. So what is next? Next is resolvent kernels. What are resolvent kernels? Another special kind of kernels. Suppose solution of integral equations. The first equation is Volterra. The second is Fredholm. Again, these are very well-known integral equations, so that's why we are considering them again and again. You might have listened to these two words now 100 times maybe, and past 1 hour, right? Volterra, Volterra, Fredholm, Fredholm. So these are very basic equations. That's why we usually mention them again and again. All right. First equation is Volterra equation of second kind. Second is Fredholm equation of second kind. And let's say their solutions are given by these integrals. All right. We don't know the solutions, but we are just assuming. Let's say their solutions are respectively ux is equal to fx plus lambda times some integral, ux is equal to fx plus lambda times some integral, and you are again getting some kind of function here. See, r, x, t and lambda. This r is depending on x and t as well as lambda, because you are solving, so this lambda is a parameter in your equation. It may be appearing in this r. We don't know how to solve the integral equation yet. Alright, so don't worry about that. How they come, where they come from, we don't know. Alright, so what we are emphasizing is, let's say somehow we got solutions, and solutions also have integrals in them, but now you are getting some functions r, x and lambda. It depends on x and t variable, then lambda parameter. Similarly, this gamma, x, t and lambda, these are called resolvent kernels. Then r, x, t, lambda and gamma, x, t, lambda are called the resolvent kernels or reciprocal kernels of the given equation. Alright, they are called the resolvent or reciprocal kernels of the equations. Alright, when we will go into the details of how to find the solutions of integral equation, you may see these r and gamma coming, alright, in your processes, in your solutions. So right now you don't have to worry about them, how we got them here, or where did they come from. We don't have to worry about that for now. Alright, so just assume that these are the solutions, and in solutions, if you are getting something in integration, that kernel is called resolvent kernel. Alright, or reciprocal kernel. We have two names for them. So next is helping tools for integral equations. Of course, we will be studying integral equations in next lecture as well. So what can be, or what should be, the helping tools for the integral equations? Alright, so that will be our last topic for today's lecture. First rule, first helping tool is a rule that is called Leibniz rule of differentiation under integral sign. How we can differentiate under integral sign? Because we have to get rid of integrations. So it means we need to derivate somehow, differentiate this equation. If you differentiate, then how that derivative affect the integral term, or how it affects the function inside the integral term. Alright, so these are our main questions. So let f x t and partial f by partial x are continuous functions of both x and t, and let the first derivatives of gx and hx be continuous. So you have three conditions here. First of all, fxt is a continuous function. Its derivative with respect to x is a continuous function. fx and gx are also continuous. Their derivatives are also continuous. Then d by dx of gx to hx, you have gx and hx are appearing in the limits. You see, gx and hx are appearing in the limits, and you are taking the derivative d by dx from gx to hx, and you are taking the integral of fxt dt with respect to time. Important thing to note here is integral is with respect to t, and the derivative with respect to x. Alright, it's not with respect to t. So that's one thing to be noted. We have replaced this fx, you see, fxt here by the derivative partial f by partial x, but then we are adding partial f plus hx dh by dx minus fx at gx at dg by dx. This is the Leibniz rules for differentiation under the integral sign. What we did is we basically differentiated this function, you see here, right, fxt dt, we have differentiated it inside, plus we took the upper limit, you see, we took the upper limit hx and replaced it in t, f of x t, t is being replaced by this upper limit h of x, and then minus the lower limit. You have done this in fundamental theorem of integral calculus, right? When you solve a definite integral, what you do? You replace upper limit minus lower limit. So this idea is coming from exactly that theorem. Alright, so what you did is you replaced t by h of x and you multiplied by the derivative of h. Similarly, you replaced t by gx and multiplied by the derivative of g with respect to x. Alright, so these two terms are coming here. Let's say if g and h are constant functions, they are not depending on x, they are just constant, then these two terms will drop out. dH by dx will become 0, dg by dx will become 0, and you are left with only this first term. Alright, so d by dx of g to h fxt dt is g to h partial f by partial x dt. Similarly, you have another tool. If you have more than one integral signs, you can reduce multiple integrals to just one integral. If you have more than one integrals, formula to reduce the multiple integrals into a single integral. If you have more than one integral signs, then how to reduce them to single integral? Here is the formula. You are going from a to x, a to x1, a to x2, so on up to a to xn minus 1, fxn dxn up to dx. Of course, you are integrating with respect to xn, xn minus 1, xn minus 2 up to x1, and then dx as well. So there are n integrals. So we can change this by single integral a to x, x minus x1 power n minus 1, fx1 dx1, and we divide by n minus 1 factorial. Alright, so this is a simple formula that reduces multiple integrals to just one integral. This can be a very helpful tool in study of integral equations. Alright, so these two are rules of integral equation. They may help us in integral equations, in solving integral equations, or in further studying the integral equations. Alright, so let's summarize what we have done today. Alright, first is we studied linear operators. What are linear operators? What are the properties, linearity properties? Whatever satisfies that linearity property, we will call it linear operator. Whatever doesn't satisfy it, that's non-linear scenario. We went on to study integral equations. In integral equations, we gave you the general definition, what are the integral equations, and then some special kinds of integral equations, classification as linear and non-linear. That was our first classification. Then we classified some equations as Volterra types, where your limit of integration is from a to x. Then we studied some integral equations of Fredholm types, where your integral limits of integrations are constant. Alright, and then we went on to study the kernels. What are the special kernels? We studied symmetric kernels. We studied separable kernels. We studied iterated internals. We studied resolvent kernels. We studied difference kernels. Alright, so these all were the special kinds of kernels appearing inside the integral sign of integral equation. So integral equations and kernels, they have very good relationship with each other. Alright, so every time you write an integral equation, you get a kernel there. So if they are of special types, special kinds, of course that will make our life easier. If they are just random kernels, difficult kind of kernels, of course that will make our life harder. Alright, so we will try to stick with those kernels and try to study the integral equations. Then we have helping tools for integral equations, and I studied two rules. First was Leibniz rules. Leibniz rule for differentiation inside the integral sign, and then converting or reducing multiple integrals to just one integral. Alright, so I hope these things were clear in our lecture, and I went through them quite briefly, and I have explained everything. I tried at least to explain you guys everything, and it's not a very difficult topic. Actually, the whole course is not very difficult. If you, whenever you listen to this lecture, you go through this lecture, try to consult books, try to go through the lecture same day so that you don't forget it. Alright, be prepared for the next lecture. Of course, the things which we are studying in current lecture, they will be used in coming lectures. So it's a very good idea to go through the first lecture, bring out any unclear things, try to clear them up, try to contact your tutors, try to contact us, and make those things clear and understand them well before going on to the next lecture. Alright, so that's my suggestion, because it's a very first lecture, so I hope you enjoyed it, and I hope that I was clear enough in explaining the concepts used in this lecture, and if you have any feedback you can send them to us and I'll be happy to answer. That is it for today's lecture. We will continue with the integral equations next time. Alright, we'll continue with integral equation next time and see how far we can go. We'll try to model integral equations. What is the background, where they come from? That will be our next question. We will be maybe solving some differential equations and we are ending up getting integral equations. That might be the scenario. Alright, so integral equation is of course a very big topic. It is a full course in itself. So we will not be doing the whole course here, but we will be getting enough knowledge, enough basic knowledge of the integral equations. If you encounter these integral equations anywhere in your studies through this course, hopefully you will tackle them down. Alright guys, that's it for today's lecture. Thank you so much for being with me, and I hope everything is clear to you guys. I'll see you in the next lecture with integral equations, with more details and more stuff on integral equations. That's it. Thank you so much, and Allah Hafiz.